Okay, we're trying to find some information about the integral around this curve, this total curve here, consisting of the rectangular boundary of this, the boundary of this rectangular region, the integral of f dot ds, which comes down to the integral of m dx plus n dy, as we've seen numerous times and as we observed on the previous clip. And we also have observed that the integral over this entire curve can be broken into the integrals over the four subcurves, the path C1, path C2, the path C3, and the path C4. Now we want to assemble some of the information we obtained previously about the values of this function, especially in terms of our sample point. So we're going to say, okay, let's again invoke our sample point, xi star yj star, and let's assemble the information we have related to the behavior of this function at the sample point or at coordinates of the sample point, and see if we can come up with expressions for these four sub-integrals, which of course you see I've already written down, but let's go back and see where they came from. Recall that the sample value of our function on this part of the curve, which we're now calling C1, was just f at xi star y, and m and n evaluated at that point. Along the upper part of the curve, which would correspond to our C3 portion of the boundary, the value was f at xi star y plus delta y, with m and n evaluated at that point. The xi star is the same between here and here. The y changes from y to y plus delta y. Similarly, between this side and this side, our x value changes from x plus delta x to just plain x. Our yj star remains the same between these two sides. When we put that information together, we find first that the integral over C1 of f dot ds, which of course is the integral of m dx plus n dy over this part of the curve, just reduces to the integral of m dx. Reason being that there's no change in the y coordinate. This is purely, this curve goes purely in the x direction. Since there's no change in the y, the n dy contribution must be 0. Now, what's the integral over C1 of m dx? Well, that's approximately equal to the value of the, well, that's equal to the average value of m on this interval, and the average value is going to be represented by the value of m at the sample point. Now, the sample point might or might not be the best point at which to find the average value. Most likely it's not. However, if delta x is small, we don't expect m to change by much with respect to x, so that we can use this approximation m of xi star y as the average value, multiply that by delta x, and get an approximation to this part of the integral. Similarly, up here, we can do the same thing. Evaluating m at xi star, this time at y plus delta y. We multiply this presumed average value by our negative delta x, and we get an approximation to the contribution to the entire line integral of the C3 part of the curve. And we can write down similar expressions for, for the integral over the C2 part and the C4 part. Over the C2 part, x remains constant. It's x plus delta x, meaning that the dx is going to be 0 on this part of the curve. There's no change in x, so that the m dx part goes away. The integral is just the integral then of n dy, which is approximately equal to this presumed average value of n times delta y. And very similar over here. using these approximations, we can write down our approximations to the integral of f dot ds over the curve. And here we just have the expression for C1, the expression for the integral over C2, the expression for the integral over C3, the expression for the integral over C4. Now we're going to rearrange these expressions a little bit. We'll put our two m factors together, our m contributions, because we can factor a delta x from the m contributions. And similarly, we can factor a delta y from the n contributions. So we write the same expression that we see here, same expression we see here for the integral of f dot ds. And we write it like so. And you can look back and verify that this is exactly the same expression as before, and that we can factor delta x out of our first two terms now, and we can factor delta y out of our last two terms, so that this expression is very easily seen to be equivalent to the previous expression. So our integral of f dot ds is approximately equal to this, and this is equal to this, but this is only approximately equal to this. Now the payoff to this argument is down here in red letters, but first we want to digress to this observation. Make sure everything's on the screen. Okay, so we see m of xi star y plus delta y minus m of xi star y. When we subtract a function at the value of an expression at y plus delta y, well, subtract the value of the expression at y from the value at y plus delta y, that should pretty much remind us of the definition of a derivative. Remember that if we do m of xy plus delta y minus m of xy divided by delta y, and take the limit as delta y goes to 0, we just have the expression for the y derivative of m. That observation is pretty much equivalent to the statement that, in that case, this difference quotient here is approximately equal to my evaluated at x, yj star. Now, we have y's here. Where does the yj star come from? Remember that we're considering this integral over a small delta x by delta y region with an xi star yj star sample point, so that when we consider this difference on that interval, our y values are all pretty close to our y sub j star. So this approximation here simply assumes that y lies between, or that yj star lies between y and y plus delta y, that is, that yj star is some point within the interval. If the interval is small, there's very little variation in the value of my, so that my at x, yj star can be approximated by this difference quotient. It then follows, of course, that if we multiply my at x, yj star by delta y, we get this difference. So that m of x, y plus delta y minus m of xy should approximately be equal to my at x, yj star multiplied by delta y. In vernacular terms, we're just multiplying an approximate average rate of change of m with respect to y by the change in y. And that's going to give us the change in the value of m. Now in this particular expression, x takes the value xi star, which brings us right into the region that we're considering, the region bounded by this rectangular curve C, this rectangle. Okay, so that instead of just an x, y, we're going to make it an xi star y, and the y, of course, can be sampled by the yj star, so we're going to be able to say that this expression here is approximately my of xi star yj star again yj star just being somewhere between y and y plus delta y, multiplied by delta y, and of course that's multiplied by our delta x. Now we can make an analogous argument with the n function, and we can come to the conclusion that, well, let's just look at this and see if we can see that if we subtract n of x yj star from n of x plus delta x yj star and divide that by delta x, then we have our derivative of n sub x, our x derivative of n, so that this difference is approximately equal to the representative value of n sub x being the rate of change of n with respect to x, multiplied by the delta x. That's going to give us the change in the value of n between these points, and this expression should be equal to this expression. We multiply by the delta y, we get this. Now we notice that we have a factor delta y delta x here and a factor delta x delta y here. So let's just factor out delta x delta y and see what we have left in the middle. And that's just this. And just what is this? Well, this is the negative of our my function evaluated at our sample point plus our nx function evaluated at the sample point multiplied by the area of the region. Well, the area of the region we can represent by a delta A. Now I should have written a delta instead of a D, so I'm going to quickly stop and fix that. Okay, so once again our delta x delta y becomes a delta A, an area increment, just the area of our rectangle. And what do we have on the inside? We have my at xy, nx at xy. If we take the limit, that should have been a D. I have to change that back. Lost track of the forest for the trees here, but we're taking the limit of this so that this is going to be approximately equal to the integral of this expression over the area, and the delta x delta y is a delta A, and when we take limits we get a dA. Now I haven't gone through the details of proving it, but I'll simply state that as delta x goes to 0 and delta y goes to 0, the approximation approaches equality and this statement that basically says the average value of negative my plus nx based on the values of these functions at the sample point becomes the actual average value, so that we can replace this expression with the integral again as delta x and delta y approach 0. For the completely rigorous argument, you should consult your textbook. But in any case, we've shown, at least a high degree of plausibility, that for this small region, the integral of f dot ds over the boundary of the curve is equal to the integral of this my plus nx function integrated over the entire rectangle, over the interior of the curve. So let's emphasize this is the interior of the rectangle. This integral is taken over an area region. So we have an integral over the boundary related to a double integral over the inside, the area of the region. And that's kind of actually an astounding result.